Athar, can you see my screen? Okay. Okay, so today we'll start about the other strengthening mechanisms. So, in the last week, we studied about the precipitation hardening. Today, we'll discuss solid solution and solid solution hardening and the strain hardening. Okay. So, the solid solution hardening comes from the solute atoms added in the primary metal. Like copper, nickel, aluminum, and copper, aluminum, silicon, means any other alloying element rather than the primary element is the solute in the matrix. So the solute atoms affect the means the strength, relative strength of the primary metal. So but the solid solution in solid solution, one is the solvent metal and other is solute element. So the size and concentration of solute element determine the level of strengthening in the solvent metal. So as compared to the size, if the difference in size is very large. So, as the size is very different from the solvent metal atom, so because of that size difference, they create strain field around the matrix. So, like if it is very small solute atom and very big solute atom, so these atom will create a strain field in the primary metal matrix, and these stress field created by these particles, these atoms interact with dislocations and pin them. So as the dislocations got pinned from the solute atoms, uh, we have to apply more stress for the deformation to continue. So that increase in stress required increases the strength of the material. Yes. Yeah, so in that case, the strengthening will be less. Yes. So if size difference is not sufficient, then the strengthening will not be much. Means it is not significant. Okay. And the strength is generally yield strength. So the two type of solute atom. So the solid solutions are generally two types. One is the substitutional and interstitial. Substitutional means the solute atom replace the uh, atoms from matrix, and interstitial solute atoms sit on interstitial spaces between atoms. So the stress field generated by these two means the substitutional and interstitial are different. Means the substitutional solid solution generate spherical distortion or stress field. Spherical stress field. While interstitial, as we know that the interstitial sites are generally uh, known as the octahedral and tetrahedral. So the octahedral and tetrahedral is not symmetric in size, so they generate a symmetric stress field. So the one more thing about the solid solution hardening, that the substitutional solute atoms they create spherical stress field and only interact with edge dislocation. Because and so one more thing, and the interstitial interact with both edge and screw dislocation. Yeah, so one more thing I have to tell, like the why the substitutional solute atom interact with edge dislocation and interstitial solute atom interact with edge and screw dislocation. So because the substitutional stress field of the substitutional solute atom uh, have two components, means it is interacting with edge dislocation. So if we talk about the stress field tensor for the edge dislocation. It is mentioned as principal stress elements sigma x, sigma xy. So in this tensor, we have principal normal stresses sigma x, sigma y, and sigma z, and only one shear stress sigma xy. So these components generally lead to distortion, distortional, and hydrostatic stress. And interstitial atom uh, and the uh, for screw dislocation, the stress matrix is means all principal elements are zero, and the shear stress components are only in the YZ and uh, XZ plane. So these are shear components only. So shear component only uh, result in distortional stress or deformation, we can also say, because the distortional and hydrostatic stress further leads to deformation, help in deformation of the material. So distortional field. So this distortional field in the screw dislocation. So interstitial atoms in the in because the screw dislocation. Yes, so for this, the edge dislocation only have the distortional and hydrostatic stress. So that's why the substitutional atom interact with only this edge dislocation. And for the distortional field, interstitial atoms can here also distortion, and for the screw also distortional will work. So yeah, so for this is for the interstitial atoms and edge and screw dislocations. And if we talk about, so this is the substitutional interstitial atom behavior with the dislocation, and the concentration, if we talk, so it is easy to understand, like if we increase the concentration, the level of strengthening also increases. Okay. Yeah. Okay. So next is the grain boundary strengthening. So grain boundary strengthening means what is the effect of grain size. So if we have so the uh, basic phenomena of grain boundary strengthening we can understand from a grain boundary. Uh, this is the slip plane, and dislocation is gliding on this slip plane from this point. And here we can say some uh, dislocation generating source is there. So dislocation is generating and moving on the slip plane. So as it come on the grain boundary, so the we know that the atomic orientation from one grain to another grain changes. Like if atoms are arranged in this direction in one grain, and in the second grain they are arranging like this. So when the dislocation come at the grain boundary, uh, they face difficulty in passing the changing their slip plane. So the difficulty in changing slip plane, uh, so they cannot cross this grain boundary and enter to the grain 2. So they accumulate, means dislocation stays here, means it is facing the applied shear stress in this direction, and as it accumulates here, it also faces some resistance force from the grain boundary region because of the disorder region at grain boundary. Means it is coming from a different ordered region in grain 1, and it is coming to the grain 2, which also have different atomic arrangement, and at the grain boundary the region is disordered. So at this grain boundary, this dislocation also faces some opposing force in this direction, opposite. So as this dislocation accumulates here, other dislocation which is coming behind also face same opposing force. So in on the second dislocation, this dislocation, because they are of same sign, so the ripple force also act on this dislocation. So the opposing force is increasing. Uh, so the distance of equilibrium distance of this dislocation also changes as we move away from the grain boundary. Means the first dislocation is here, and second dislocation will be here, and so it is x x1, it is x2. So x2 is greater than x1 because of the forces they are experiencing on the slip plane, and because of the this opposing force from the grain boundary and accumulating dislocations. So this force from the grain boundary create a back force in this direction. So the to be in equilibrium, the applied stress toy and the this back stress are equal. So from this relation, the Hall pitch, these are scientists, so they derived a equation uh, with this back stress uh, concept. So the final yield strength of a material can be represented. So it is directly proportional to the square root of uh, d. D is the grain size. in micrometer. So if we further equate this equation, so this can be written as sigma naught plus some k constant. K is the locking parameter, and sigma naught is the lattice friction stress, the dislocation experiencing during the motion. So this formula is derived from the Hall pitch, and this defines the grain boundary strengthening in the alloy or in the metal. So it means if any metal which is does not have any other strengthening mechanism but finer grains. So because of the presence of finer grain and fine microstructure, the strength of the material will be high. So as the grain size decreases, the yield strength will increase. Means the because the grain size is reducing, so there will be more opposing force uh, for the dislocations. So we will solve some questions, means, example question, and then we'll go to the assignment question also. So the first question says the yield strength of a low carbon steel depends on its grain size. The following data have been reported, means the grain size is given for two yield strength. So for estimate the yield strength of the same steel treated to give a grain size of this 0.0156 millimeter. So to calculate the yield strength at another grain size, we have to first calculate the other parameters in the equation, means sigma naught and k. So if we take the first value, we can take it as 25 micrometer also. Okay, so 205 equals to sigma naught plus ky 25, and second equation 125 equals to sigma naught plus k by root 150. So if we differentiate these two equations, So it is 1 by 5 is 0.2. Yeah, and it is 0.0816. So it is around 80 by 0.1184, and it will be 675.7. And the uh, unit for this will be MPa. MPa divided root micrometer. So we got value of K, and we can find sigma naught 205 minus 675.7 divided root of 25. So sigma naught will be 135. So it is coming 70 MPa. So we know the value of K and sigma naught. So we can find the yield strength at this uh, grain size. 70 plus say 60 and divided square root of this grain size. So we can find the yield strength from this. Okay. So next question is on the if yes. Yeah, we can change the unit also, but we are considering the yield strength in ampere. Yeah. So means the grain size. So it is generally find in micrometer only. Means the most of the metals have grain size in microns. Only few materials like superalloy, nickel superalloys and zinc have a very big grain size in millimeter. So next question is, if a steel has a value of sigma I 150 MPa and K is 0.7 MPa, square root of a meter. Yeah, we can take it. Here it is given square root of meter, so we will take the grain size in meter, or we can convert in micrometer to meter also. So in this question we have given ASTM grain size 6. So for this we can calculate the grain size from the formula. So here sigma I is the sigma naught only and K is given. So ASTM's number 6. So we have to take formula ln Na is equals to G plus it is it is American standard for testing materials. So American standard. So grain size also have some means standardization under ASTM. So the different grain size is given numbers also. So we can convert this number into actual grain size in meters or micrometers. So the formula to calculate grain size from the ASTM number to micrometer is ln Na uh, G plus 2.9542 divided by 1.4427. So G is the ASTM number here. So Na is the uh, grain number. So and the grain size is calculated as the square root of Na. Okay. So from this formula we can get Na as so G is 6. So when we put in this and take exponential of this term, so the Na will be 496 into 10 raised to power 6 per meter square. And if we take square root of this, it is per meter square. So it will be 1 by meter. So when it comes from the square root, it will go in meter. So the grain size will be around 44.7 into 10 raised to power minus 6 meter. So it is coming micrometer only. So now we can use the Hall fetch equation. So sigma naught is 150 plus K is 0.7 MPa in root meter divided by root of this 44.7 into 10 raised to power minus 6 meter. So this will give 150 plus 104.3 ampere. So the final yield strength will be 254.3 ampere. Okay, so we'll go to the assignment questions now. Yeah, one more thing I have to tell. In the solid solution strengthening, if modulus of the solute atom is different from the solvent, there is large difference from the in the elastic modulus. So that difference in elastic modulus also result in hardening of the solvent metal. So can you see questions? Okay. So first question says, which of the following are the primary mechanism responsible for solid solution strengthening in metals? So can you guess the answer? Yes, lattice distortion and hindrance to dislocation motion. Second question is, which of the following statements are correct regarding strengthening mechanism in materials? So first option say the matrix and precipitate must have same crystal structure. I mean, it is not possible every time. So the second option say the matrix and precipitate may have same crystal structure. So it is means this statement is correct. Means they can have same or different crystal structure. Okay. So this option is correct. Next is the extent of solid solution strengthening increase with increase in solid concentration. So this is also correct. Yeah, and fourth option is saying it is independent, so it is wrong. So B and C is correct. Third question says like which of the following statements are correct regarding stress field caused by solute atoms? Yeah, one is correct. Yeah, four is correct and three is also correct. When it is saying a small substitutional solute atom produces a spherical stress field. So both small and large solute atom create spherical stress field. Means there is no difference between small and large the large solute atom. Only the stress field amount will be different, and it will be different in the dislocation slip plane. Means it is above or below. So the large solute atom generally sits below the slip plane of dislocation. Means we can say like dislocation. So this is this is the extra half plane, and this is the positive edge dislocation. So below this slip plane, the atoms are squeezed. When a compressive stress field is there, and in the uh, bottom of the slip plane, the atoms are spaced widely, so there is tensile stress uh, at the below the plane. So the large atom will prefer to sit below the slip plane, and the small substitutional atom will prefer to sit in the compressive region, means above the slip plane. So, and both large and small substitutional solute atom create spherical stress field, while interstitial create non-symmetrical stress field. So, the third option is also correct. Yes, means the stress field will be like this. I will change the pen. ink is like in this. And the interstitial, as the interstitial sites are octahedral and tetrahedral. So because of the size of this interstitial, the stress field will also be non-symmetrical for interstitial atom. Okay, so we'll go to next question. Okay, so fourth question says, which of the following factors influence solid solution strengthening in materials? Yeah, elastic modulus, size of solute atom, concentration, and whether it is substitutional or interstitial. Next question says that which following statements are correct regarding interaction of solute atoms with dislocation? Yeah, option three is also correct. Means the interstitial solute atom uh, um, means they contribute more strengthening. So the strengthening level in inter interstitial is around 3 times of shear modulus, and for substitutional, it is G by 10 strengthening level. So for interstitial, it is higher. Okay. Next question is, which statements are correct regarding the interaction of solute atoms with dislocations? Yeah, one and three is correct. Sorry. Means smaller will sit in compressive and larger will attract in the tensile region of the lattice. And this fourth option is also correct. Means impurity atoms. Impurity atoms are the solute atom only. Are attracted to dislocation to reduce the overall strain energy of the lattice. Means the overall strain energy of the lattice they reduce to make the dislocation immobile, as the this dislocation stress field and solute atom stress field. Means the interaction of both these uh, means we can say that like in the substitutional also, they try to sit in the large atom will sit in tensile, and small atom will sit in compressive. So because if they do not do the same thing, means if large atom sits in compressive, so the stress field will increase in the above the slip plane. And similarly, if a small atom sits in below slip plane, so that will create more tensile stress field. So they sits opposite in the opposite stress field region to reduce the strain field energy and to stabilize the dislocation so it does not move. And if dislocation does not move, the plastic deformation will not occur in the material. So this option is also correct. Sorry, the fourth option is correct. Impurity atoms are attracted to dislocation to reduce the overall strain energy of the lattice. So 1, 3, and 4 is correct. So next question, it is asked like what is the velocity of dislocation when the applied strain rate is 3 into 10 raised to the power minus 7 per second. The dislocation density is 10 raised to the power 8 per meter square, and the magnitude of Berger vector is 3 angstrom. So the relation for with strain rate and dislocation density velocity is given as, this is epsilon naught equals to rho b v. So rho is the dislocation density, b is Berger vector, and v is the velocity of dislocation. So we need to find this velocity. So strain rate is 3 into 10 raised to the power minus 7 per second divided dislocation density 10 raised to the power 8 per meter square, and Berger vector 3 angstrom, 3 into 10 raised to the power minus 10 meter. So this will be equal to 10 raised to the power minus 5, and the unit will be meter per second. So third option is correct. Next question is, Luder bands are a region characterized by. So Luder bands generally form in the tensile test specimen because of the stress concentration in some region. And these are generally formed in the region where dislocation density is high. So the higher dislocation density will be create a localized deformation. So this localized deformation in the tensile specimen is uh, generally can be seen in the on the surface of the tensile specimen in microscope. Means we can see like if we, so these type of lines are observed as the Luder bands. So these occur because of the stress concentration in some region, high dislocation density, accumulated slip planes. So accumulated slip planes also favor deformation. And next, and fourth is low density, so it is wrong. And so first, for 1, 2, and 3 is correct for this. Okay. The ninth question is, a grain size reduction leads to improvement in. So grain size, which affects which property of the material? Yeah, strength at room temperature and hardness. And Young's modulus is microstructure insensitive. And uh, creep strength is inversely proportional to grain size. Means if grain size, sorry, no, directly proportional to grain size. Means for coarser grain size, the creep strength will be good. And for small grain size and finer grain size, the creep strength will be poor. So only first and three is correct. Okay. So next question is numerical for an alloy. The yield stress is 300 MPa when a grain size is 196 microns. What will be the yield strength when the grain size reduced to 121 micrometer, given the frictional stress is 150 MPa? So we have given sigma naught 150. So means this is easy. We can get the K value easily. So root 196 is generally 14. So and we have to find yield strength when grain size reduced to 121 micrometer. Sigma naught is 150. K is 150 into 14 divided square root of 121. So this will be 11. And when we equate this, so this will be equal to 341 MPa. Okay, so this is easy question. Okay. Next question is same as previous, only the values are different. So here sigma naught is 120 and these are the initial values. It's 12. So 120 into 12 it is the K value and yield strength and at the other grain size will be 120 plus divided by root of 100. So it will be 10. So 120 plus 144. So this will be 264. So second option is correct. Okay. Yeah. So these are the assignment questions. And so yeah. So this is all for today's session. Do you have any doubt? Creep strength is uh, generally described as the strength of material when a constant stress is applied on the material. So, if any component or material is subjected to a constant stress for long time, so the deformation occurring due to that constant stress for long period is known as the creep of the material. Means creep is generally defined as the long-term deformation for a constant stress. Mean in generally the industrial application, uh, the pressure vessels are subjected to the constant stress. So in that condition, creep strength of the material should be very high. And the constant stress and the thermal conditions also lead to creep deformation. Yeah, so the thermal stress and constant stress is related to the creep strength of the material. Okay. Any other doubt? Okay. Okay, then we can end this session. We'll meet in next week. Thank you.